My name is Muhammad Al-Banna and I'm going to teach you this term, the Microprocessor Systems course, CC 421. Each course you are taught has ILOs, intended learning outcomes. These are the milestones of the course. You may forget the details of the course, but you should always remember these ILOs. And I'm going to list the ILOs of the Microprocessor Systems course. Alright, the first ILO, after taking and passing this course, you would understand how computers work, the general working of computers, and you should comprehend the internal structure of computers, CPU, memory, and buses. You should always know two main concepts in dealing with computers and programming, which are pipelining and prefetch queue. You should be aware of these two terminologies and techniques used in dealing with computers after taking this course. We'll focus on the 8088, 8086 Intel's processors in this course, and you should be aware of the internal structure of these microprocessors, the different registers and memory segments used by Intel's processors. You should as well be able to differentiate between logical memory seen by the programmer and physical memory designed by the hardware engineer. In Intel's processors, they divide the memory into different segments and assign a specific job for each of these segments. You should be aware of these different segments and the different jobs and uses of these segments after finishing the course. Okay, we'll go over some hardware, the pin configuration of the processors, and the hardware to be interfaced with the processors, like different memory chips and ILO ports. Alright, the eighth ILO deals with the different addressing modes. The processor is useful when it is interfaced with memory and IO ports. Each memory location and each IO port should have a unique address, and there are different modes of addressing these locations, memory locations, and IO. You should know the different addressing modes of Intel's processor after passing this course. In dealing with processors, data in and data out, there should be some way to detect errors, if any, and to correct them. Techniques of detecting and correcting errors will be discussed in the course, and this is a milestone or an ILO of the course. How memory and IO ports used and interfaced with microprocessor, this is a specific topic to be focused on in this course. Alright, eventually you would have some lab sessions to exercise what you are being taught in the course, different instructions, and how processor is interfaced with other chips, and how data are going in and out through the processor. These skills and techniques will be taught to you through some lab sessions. Okay, there are 4 groups of you, 2 of which will be taught the course by myself, and the other 2 will be taught the course by Dr. Hania Farag. And here are suggested timetable of the course and suggested office hours of the course. We have some TAs to help us in teaching the course and to guide you in the lab sessions. The topics to be covered in the course are divided into 2 portions. A software portion, chapter 1 is the general knowledge of computers. Chapter 2, Introduction to Intel's Processor 8088, 8086. And Chapter 3 will discuss the addressing modes. Chapter 4, the program control instructions. And the other portion is hardware, through which we are going to introduce the pin configuration of the 8086, 8088, and how are they used to connect the processor to supplies and to interface it with other chips, and memory interfacing. Then we finish the course by focusing on the I/O ports and how to interface them to the processor. The textbook used in this course is the Intel Microprocessors 8th edition, written by Barry Bray. This book lists all Intel's processors throughout the time. And the grading policy, we assign 30% for the midterm, 20% for your lab sessions, and 10% for a project. By the end of the term, you will be assigned a project to do. And finally, the final exam, written exam, would be out of 40%. Okay, let's start the course. The introduction chapter 1. The introduction chapter. Okay, we have two big microprocessor families, the 80 series by Intel and the 68 by Motorola. This course will focus on the Intel processors used in PCs, personal computers. Okay, and if you look at the timeline, the evolution of the Intel processor, you will find the 8080 processor introduced in 74 and so on. 8085 in 76, then 84, 86 in 89. And if you look at this table, as time passes, configurations either stay as is or goes up. For example, the physical memory in 74, 64K, and 76, 64K. In 78, they were able to reach the 1 megabytes of memory. So it's sizable memory locations. This is in 78. And the first time in history, they were able to reach the 1 megabytes of memory. In 82, 16, in 85, 4 giga, and 89, 4 giga. As you see, as the time passes, the configuration is either still as is or goes up, except for the data bus, as it goes down from being 16 in 78 to be 8 in 79. And there was a story behind this, because people bought hardware which was expensive at that time, with the processor around the processor 8085, which used an 8-bit data bus. When Intel invented the 8086 in 78 with twice as much higher speed, people who invested and paid a lot of money in interfacing 8088, 8085 with hardware equipment wanted to take advantage of this high-speed processor, but all their hardware are interfaced with an 8-bit data bus of 8085. So what Intel did, okay, they introduced the 8088 processor in 79, whose configurations is the same as the 8086, except for the data bus. They went down to 8-bit data bus in order not to lose these customers, which can now enjoy the high speed of the 8086 without changing the hardware equipment, which was interfaced to an 8-bit data bus. Okay, one more thing you should notice And look in this at this table. The processors were given numbers 8086, for example, 8086, 8089, 8186, 286, 386, 8486. So this is the last processor that was given just a number. All right. In 1995, the Intel found that in order to sue people who steal their intellectual property, they cannot legally go after them if their product is given only a number. So they had to introduce some names beside the number. Pentium Professional, Pentium 2, Pentium 3, Pentium 4, Core i2, Core. So they have to give, besides the number, they have to give some word in order legally to sue whoever tries to steal their intellectual property. Okay, here is a table to show the latest processor introduced by Intel in the third quarter 2020, Core i9 that has 10 different cores, as if they produced 10 independent processors on the same chip, and you can run up to 20 threads at a time and to get the results simultaneously. And here are the processors for the mobile. You can follow the evolution of Intel's processors, and you have here the URL. You can go there and find more information if you wish. Okay, the execution time of Intel's processor for the 8086, it was also a breakthrough regarding the execution time. They have entered the nanosecond range. Previously, we were talking about the microsecond range, but here in 8086, they introduced processors whose access time is in the nanosecond range. So the advantages of these processors, you have hardware multiplication and division, which means you can multiply and divide numbers by hardware. You present the first number, then the second number, instantly you get your instantaneously you get your result. So you don't have a program to run to get you the result of multiplying two numbers. You just have a hardware piece, a multiplier, provide the first number, the second number, you will get the result. Okay, we said it previously, you have large addressable memory. This is the first time they enter the 1 megabytes range of memory. And you have a large number of registers, which makes your program run faster. Registers are temporary memory locations beside your processors, and their access time is in the nanosecond range. This will make your programs and codes run faster. Okay, how do processors execute codes? How they fetch and execute codes? The first, you fetch for an instruction. You get the instruction, pass it to your instruction decoder to get it decoded in order for your ALU to know what to do exactly. Fetching an instruction should be followed by getting operands, reading operands from the memory, the data required for the processor to run this instruction or to execute this instruction. Having your instruction and operands, your processor can go ahead and execute this instruction. Okay, good. Previously in 8085, this was done through the 8085 has a CPU unit and a bus unit. Okay, to run a code, your CPU will fetch for the current instruction by loading the address of this instruction to your bus. So while your CPU is fetching, your bus is busy being loaded with the address of this instruction. Having done this, the instruction is now inside your CPU. your CPU will read the data required to execute this instruction, reading the data to execute this instruction. By reading the data, your bus would always be busy by being loaded with the address of the data. Now you have the data ready, the instruction ready, your CPU unit can now execute the instruction and your bus will be idle. No address is loaded, no active address is loaded to your bus. So the bus waits for your CPU to execute the instruction, then the cycle is repeated. Fetch for the instruction, write the result to your memory, and execute this instruction, and your bus will be idle. So there is some time interval through which you don't use the hardware available, which is the bus. This is why they try to make use of this bus during this idle interval. By doing so, in 8086, 8088, the steps to execute an instruction will be as follows. This is the normal operation of 8086. They divided the CPU into two units, execution unit and bus interface unit, along with the bus. Your bus interface unit is responsible for loading the address of the current instruction, of the instruction to be executed currently. So its responsibility is to fetch for the instruction by loading the address to the bus. So both BIU fetch for the instruction, your bus is busy. Then it's the responsibility of your BIU to read the data required to execute this instruction, and then passes to the execution unit to execute this instruction. Okay. While executing the current instruction, your BIU and bus will be busy in fetching for the next instruction, fetch and write the result to the memory, and so on. Now you don't have your bus will always be busy in dealing with addresses to get instructions and data. And this is a schematic diagram to show you the relation between the bus interface unit and the execution unit. Here is the outside memory, so your bus can get instructions as well as data from the outside memory to your inside of your microprocessor, reading, writing data, and the instructions are stored in a very small piece of memory called the prefetch queue in such a way that once your execution unit has finished executing some instruction, the next instruction would be loaded from this prefetch queue, from this piece of memory, which resides immediately beside your processor. The instruction will be fed to the instruction register to decode it and tell your ALU what to do with this instruction. Okay, so your bus interface unit is responsible for the following: to keep the prefetch queue always filled with instructions. Two, three instructions are ready, and whenever memory locations are emptied, the data are taken from a memory location, your BIU should make sure that these memory locations are always filled with instructions. Okay, they can as well generate and accept control signal, reading or writing data to or from the memory. And they can always control the data communicated between I/O ports and your processor. Okay, so they act as a window between your memory and your ALU or the core of your microprocessor. So this is the BIU. They take data from memory, pass it to the microprocessor, and the result from microprocessor back to your memory. Okay, how big your prefetch queue should be? First of all, it is of a FIFO type memory, which means the first instruction to be stored into the memory is the first to get out of the memory, because we're talking about executing a code. In executing a code, instructions are executed sequentially. The first one, the second one, the third one. So if you store an instruction first, it should go out first. If you store an instruction second, it should go out second. This is the FIFO type of memory. How big your memory should be? It doesn't have to be a big memory. A memory to take few instructions would be enough. This is why in the 8086 you have 3 memory locations, each of 2 byte wide. So all in all, you have 6 bytes of the prefetch queue. While in 8088, you have a 4 memory location, each of a byte wide. So all in all, you have 4 bytes of memory inside your 8088 processor. Good. What is the responsibility of the execution unit? It carries out instructions and tells the ALU to do and perform operations, whether it is a logical operation or arithmetic operations. So it controls the ALU and tells you the codes of the instruction and tells your ALU to do multiplication, addition, summation, or division if it does an arithmetic operation, or logically ANDing, ORing, or whatever if it does a logical operation. Okay, and the AAU execution unit has an array of registers which hold data temporarily and help your execution unit to run your code faster. Okay, we've talked about instruction registers. It receives the instruction from the prefetch queue and decodes it to tell the ALU what to do. So this is the function of the instruction register. Okay, how about the system architecture? 8086 system and 8088 system. Looking at the 8086 system, this is your 8088 processor interfaced with some memory. So the system is having an address bus of 20 bits. This is why they can access as many as 1 megabytes of memory. They are labeled from A0 to A19. Then a data bus composed of 16 bits labeled D0 to D15. Then a control bus which has 3 signals: low if the processor is reading, low if the processing is writing. So you pass a low signal to this line, RD line, if you are reading, or passing a signal to WR line to write memory to locate data to a location. And if you're dealing with a memory, you should send a high signal to this line. If you're dealing with an I/O port, you should send a low signal to this line. While the 8088 processor, the address bus is the same, 20-bit, A0 to A19, while the data bus is composed of only 8 bits, labeled D0 to D7, and the control bus is the same for reading and writing, and it is the other way around for I/O. You send the high signal, memory, you send a low signal. So this is the end of lecture 1. We'll see you on lecture